calculating the vapor pressure, boiling point, and freezing point of a solution. So why is this important? Well, do you remember those folks living in Denver? Their water won't boil at as high of a temperature as ours. Well, they can solve the problem by adding a solute to their water. Their water will then boil at a higher temperature. Up north, this is slick. All right? Ice is slick. Well, let's add a solute to the water, right? Let's sprinkle a solute on the ice. The freezing point goes down, right? There's a liquid. It's not slick here. So when the freezing point goes down, it has to be a lot colder for it to freeze, right? So it's going to have to get really cold for this stuff to freeze. Okay. But there's problems with that, right? Because if you go up north, you don't really want to buy a used car up north because, rust. Okay, the solute that they add, it's not very good on cars. So for today's predictions to work, what's going to be the new boiling point? What's going to be the new freezing point of this solvent when you add such an amount of solute? Well, for all these equations to work, the solutes have to be molecular. Now, we don't really need to worry about it because the homework is going to give us only molecular solutes. But all that means is just no ions. All right? Your solute can be something like sugar. It's a molecule. That'll work. Okay. So for all of our homework and problems today of calculating and predicting new boiling points, freezing points, and that sort of thing, only molecular solutes. How do we imagine the solvent's vapor pressure? What is a vapor pressure? Okay, here we have some water. Recognize the water molecules? This is the liquid phase, and this is the gas phase. So what can exert a pressure? Well, gases exert a pressure. And the harder they're flying around and the more hard, the faster they're traveling, right? And the more of them, the greater the pressure they'll create. So these water molecules in the gas phase, right, they're creating a pressure, and that's called the vapor pressure. And it's at equilibrium. I mean, you have boiling occurring at the same rate as condensation. So the number of water molecules in the gas phase isn't changing over time. Now, what happens to this vapor pressure when you add a solute? That's what they're trying to show over here, and probably not very well. But if you see the green and the blue spheres in here, they're trying to say, hey, we added a solute. So what is the effect on this vapor pressure? Well, it blocks it. It blocks the water molecules from leaving the liquid phase. So you end up having less water molecules in the gas phase because they're being blocked. So that means a lower vapor pressure. So whenever you add a solute to a solvent, the vapor pressure always goes down. How about here? If you only have pure water, does changing the amount of pure water change its vapor pressure? Okay, over here we have a beaker of, well, an Erlenmeyer flask of water. If I cap it and just let it set for a good long time, we'll have equilibrium between the, condensation into liquid phase and evaporation into the vapor phase. So there will be a vapor pressure in the container. And we can, since this is pure water, we can go to a table and find out what the pure vapor pressure is. If I dump out everything, you can kind of still see there's some drops here. If we wait a long time, and if these drops are still there, that means there's an equilibrium, again, between the liquid phase and the vapor phase. So the amount of water doesn't matter. It's almost like boiling point, right? Or density. The amount doesn't matter in those things. How do we determine vapor pressure of pure solvents? Or melting points, or freezing points? Well, we use tables, right? For the pure, but when you add a solute, there's not a table for that. Too many permutations. So there's 3 colligative properties of a solution when a molecular solute, and they're going to be calling those capital B, is added to any solvent, capital A. And cligative just means the more you add, the bigger the change. So if you want your boiling point to go way up, well, just add a lot more solute. First one. A solution's vapor pressure is always what? Than that of the pure solvent. Remember when you add a solute, it blocks the water from leaving the liquid phase? So that vapor pressure of a solution is always lower than that of the pure solvent. Okay? So you can calculate it. How much did it get lowered by? This number right here. Here's our pure vapor pressure, right, of our solvent. And here's XB. Remember what X was? The mole fraction. And mole fraction of what? Well, B. Remember, B is the solute. So if we look up in a table, find out what the pure vapor pressure is of the solvent, multiply it by the mole fraction of the solute, and we'll get some number, delta P, the amount that the vapor pressure was lowered by. So our new vapor pressure, right, you get the pure from the table, and then we add or subtract delta P. Vapor pressure gets lowered, so we better subtract. Okay, so that's just something you have to know, because I give you the equations, but I'm not going to tell you what to do with them. Okay, so you'll calculate how much the vapor pressure changes by, and just realize, oh, I have to subtract that from the pure solvent vapor pressure to get the new vapor pressure. Okay? The solution's boiling point is always what? Than that of the pure solvent. You add a solute, boiling points go up. Right? In fact, a solution doesn't boil until its vapor pressure reaches external pressure. And that might be more information than you need, but the idea there is since the vapor pressure is lowered for a solution, it has even further to go. You have to heat it up even more to get it to boil so that the vapor pressure is the same as the external pressure, which is atmospheric. Okay, so here's an equation for boiling point, okay, how much it's going to go up. And little b just stands for ebullioscopic. Ebullioscopic. That's what the little b stands for. Okay. So if you want to get the new boiling point, look up the pure solvent boiling point in a table, and then we add or subtract this number that we're going to calculate. Right? And this number that you're going to calculate, it's the ebullioscopic constant times C little m. Remember what that was? Molality. Right? The concentration of our solute, but in terms of molality. Moles of solute over kilograms of solvent. Okay, so back to this. Our new boiling point will be the pure solvent boiling point plus this delta T that we're going to calculate. A solution's freezing point is always what? Than that of the pure solvent. It's always, remember the ice? You throw a solute on there, the freezing point goes down. Right? It's more difficult to freeze. You have to get it even colder for it to freeze. Right? So it's going to be lowered. The freezing point will be lowered. So our new freezing point, take the pure freezing point and subtract this delta T that you're going to calculate. Okay? So there it is. Delta T would be Kf, another constant, times our molality. There's our molality again. So these constants, Kb and Kf, right? You find them in tables, but we look them up for the solvent. The solute doesn't matter. Remember, the solute is just a blocker. Like, think of it as the vapor pressure lowering. The solute just It doesn't really matter. It's the solvent. Okay. There's a lot more solvent than solute, so that's why. Overall, these colligative properties are called, okay, vapor pressure lowering, boiling point elevation, freezing point depression. If you remember the names, it just kind of helps you to remember what to do with your delta P or delta T, right? So now we have 3 more equations to add, right? Now we have 3 more equations to add to our list of equations. And just remember, this is my little Cm. That's molality. Okay. Let's try one of these. A solution was prepared by dissolving 1.258 grams of naphthalene in 25 grams of benzene. What's the freezing point of the solution? Well, what's the freezing point of the solution? So that means we're going to have to be using this expression, right? Delta TF is KFCM. And our answer then would be, we need the true freezing point, and then it gets lowered, right? So we're going to subtract our delta TF, whatever we get, from our solvent's true freezing point. Now, there's a good question. Which one is our solvent? The solvent, remember, is the one that you have the most of. So this has to be my solvent. Because look, I have 25 grams of it. It's a lot more than the naphthalene. It's only 1.2. So if benzene is my solvent, its freezing point is 5.5. Right? Its freezing point is 5.5. So I'm going to calculate that delta TF, subtract from 5.5, and I will have my answer. Okay, let's calculate that delta T. Just how much is that freezing point reduced by? Well, we're going to need a Cm, so let's get that Cm. And according to our table, well, I'll show you. According to that table, Cm is the moles of solute over kilograms of solvent. But I don't like writing it that way. If you write moles of solutes, it's not very helpful. Instead, write out what the solute is. C10H8. Moles of C10H8 over kilograms of solvent. And don't write the word solvent. Write down what the solvent is. Benzene, C6H6. It just, I think, makes the problems easier if you get into that habit. So moles of naphthalene. We've got 1.258 grams of the stuff. 1.258 grams C10H8. How many grams in a mole of naphthalene? Okay. I need kilograms of benzene on the bottom. I've got 25 grams of it. So 25 grams times 1,000 grams in a kilogram. Get about 0.39. Little m is our symbol for molality. So let's go ahead and put that in. So delta TF is going to be KF times CM. Now what do we say our KF is? Here it is. Remember that these constants, look them up for the solvent. So we're looking up for the solvent. So that's why I'm using 5.065. I'm not using that one. It has to be for the solvent. 5.065 is my KF. Times my molality. I get about 2. So put that in up here. 5.5 minus 2 is 3.5. So that's my answer. That will be the new freezing point of benzene if I add 1.258 grams of naphthalene to it. Here's another one. Calculate the vapor pressure lowering of 25 grams of ethanol when 2.85 grams of sugar is added. Okay, they want the vapor pressure lowering. They don't want the new vapor pressure. They want the vapor pressure lowering. That means find delta P. How much was it lowered by? Okay, so find delta P and stop there. Delta P is right here. Vapor pressure of the pure times the mole fraction of the solute. Okay. Now they say that vapor pressure of pure ethanol is 55 millimeters of mercury. So halfway there. Okay. Now I need the mole fraction of the solute. Okay. XB. What's my solute? Is it the ethanol or is it the sugar? It's the sugar, right? There's only 2.85 grams of it. So I want the mole fraction of C12, H22, O11. So that's going to be the moles of C12, H22, O11, divided by the total moles. .85 grams. Yeah, I got 342.34 is the molar mass. About 8.3 times 10 to the negative 3. Yeah. So this ethanol, how much did I have? I had 25 grams of ethanol. About 46.08. Oh, 0.54 moles. Okay, let's put that stuff in. Moles of the sugar, 8.32 times 10 to the negative 3. Divided by 8.32 times 10 to the negative 3. And the ethanol, 0.54. Oh, 0.015. That's my mole fraction. Okay. So let's go back up. Let's finish this. Here it is. That's my mole fraction. So about 0.83. Now remember, mole fractions don't have any units, so that's why we end up in just millimeters of mercury. And that's our answer. Okay. A 0.0182 gram sample of an unknown substance was dissolved in 2.135 grams of benzene. So right off the bat, you can see that this is our solute, and this is our solvent, because there's more of it. The molality of the solution, determined by freezing point depression, was 0.0698. Well, you should probably start writing some of this stuff down. The molality is 0.0698. Okay, what is the molecular mass of the unknown substance? Okay, what is the molecular weight? Okay, this is going to be a two-part question, because what is molecular weight? Molecular weight is, grams over moles, right? Okay, and it's this unknown substance, so it's kind of like the grams of this unknown substance divided by the moles of that unknown substance. Okay, now do you see that we already know one of these? Which one do we know? Do we know this one, or do we know this one? A 0.0182 gram sample of the unknown. Man, we're halfway done. It looked ugly, this question did, but it's really not that bad. 0.0182 grams. We're halfway there. All we need is moles. This is what we need to find. Okay, and then we'll be done. They told us molality. They told us this for a reason. Okay, because remember, what's the definition of molality? 0.0698 has to equal what over what? Do you remember molality? Moles of solute over kilograms of solvent. So let's not use the words solute and solvent, though. Moles of unknown substance divided by kilograms of benzene. Okay. Now can you see what's going to happen now? All right. We know this. Let's substitute in for it, solve for moles of unknown, and then bring it in over here. Right? Let's try it. So we'll have 0.0698 has to equal moles of my unknown divided by kilograms of benzene. It's going to be 0.002135. Okay, so take 0.0698 times 0.002135, and I get 1.49 times 10 to the negative 4 moles. Do you know how I did this so quick? All I did is I moved the decimal place over 3, because I have to divide by 1,000. So what I did is I just went 1, 2, 3. So I have 0.02135. So that's how I did it so fast. Okay, let's put in those moles, and we'll have our answer. So our molecular weight is going to be 0.0182 grams divided by 1.49 times 10 to the negative 4. About 122 grams per mole. Okay, an aqueous solution of a molecular compound freezes at a negative 0.086. What is the molality of the solution? So know these names of these variables in our equations. They want to know what Cm is. Right? They want to know what Cm is. And they're talking about this freezing idea. So delta Tf equals Kf Cm. Okay? So we're going to solve for molality. So that means we have to know the other two. And aqueous is just another word for water, right? It's in water. It's in H2O. So we need the Kf of water, and they gave it to us. What we need is a number for that delta T. Okay? They told us that it now freezes at a negative 0.086. So that new freezing point is a negative 0.086. But what's the regular freezing point of water? 0 degrees Celsius. So my delta T, my delta Tf, right, is going to be 0 degrees Celsius minus a negative 0.08. It's just going to end up being that final temperature, right? And that minus and minus is a plus. Okay. So that will go up here. Now I can solve for Cm. .086 divided by 1.86 is about 0.046. Put on the little m for the unit. Urea is dissolved in 100 grams of water. The solution freezes at negative 0.085. How many grams of urea were dissolved to make this solution? Okay, so we're after this freezing point depression. So we know this is a good place to start. All right. They are after how many grams of urea? This is what they want us to find. Now, where is that in here? Where is it at? It's in the molality. It's just in the wrong units, right? If we find Cm, remember that's going to be moles of solute, which is urea, divided by kilograms of solvent, which is what, water. Let's find this and then convert to grams. And then we'll be done. Okay, that's the game plan. Let's use our freezing point depression equation to solve for molality, and then using the molality, we'll solve for moles and get grams. So it's a little convoluted, right? So let's see if we can get it. First, let's get Cm. So my delta Tf, and remember, since water typically freezes at 0, this final temperature is delta T, so we can kind of drop that negative though. Remember, we just worked a problem like that. Equals Kf, which is 1.86. So what is my Cm? 0.085 divided by 1.86, get about 0.046. Okay, now I can use that, right? 0.046 has to be moles of urea, which is that funky formula, divided by kilograms of water. We know we have 100. 0.1 kilograms. See how I did that? 1, 2, 3. So that'd be 0.1 kilograms. So I can find my moles. 0.046 times 0.1. Now we just have to convert to grams. So I have 4.56 times 10 to the negative 3 moles of this urea, and in a mole of how many grams? So we've got 2 nitrogens. Where's my periodic table? Make sure I'm doing this right. Nitrogen is 14.01. That's what I was going to guess. 14.01. .07. So if you add up 2 nitrogens, 4 hydrogens, a carbon, and an oxygen, you should get about 60.07 grams per mole. Take that times my moles, 4.56 times 10 to the negative 3, and I get about 0.27. Okay, and that's the answer. That works. And there we go.